And welcome everybody to the Daily Space Weather. I'm your host Dan, aka smAsho, and we're starting things out looking at Stereo A's coronagraph. The coronagraph located at gravitational equilibrium point Lagrange 5. And we see an Earth vicinity coronal mass ejection right in this area. So, Stereo A is located out here at Lagrange point 5. And again, here's the view from Stereo A. You can see this loop of plasma coming out. This was also accompanied by two C-class solar flares as well as a Type 2 and a Type 4 radio burst. We won't get in depth into what that means, except that, well, there are coronal mass ejections. It's too early to determine how earthly these are going to be, so here's the view from the LASCO C2, which is located at Lagrangian point 1. Again, the LASCO C2, nothing to see yet on this as it is too early to determine the direction of this coronal mass ejection. And you might be wondering where that coronal mass ejection came from. It came from sunspot 2816, which is this C-class flaring sunspot you can see right here, and those two flares were associated with that radio burst. Actually, two radio bursts, again, a Type 2 and a Type 4 radio burst associated with this, and two C-class solar flares. And we'll probably make a second video later today about how this unfolds and what its direction is. Here's the rest of the solar disk, and what you're looking at is ionized iron here in 94 angstroms from the SDO, the Solar Dynamics Observatory. Sunspot 2817 up here is also producing a little bit of activity, as you can see there, adding to the total X-ray profile of the closest star. And we've got some close-ups here. This is the sort of the northeastern limb in 171 angstroms. And here's a composite view. This will actually show you the solar flares as well as sunspot 2817. This is actually two wavelengths. We've done a fade here between 193 angstroms and 171 angstroms to show the maximum amount of detail here. Great view of that coronal hole leading sunspot 2816. And here's a full disk view in ionized helium, 304 angstroms. And I would also note that there are a bunch of filaments down here, mainly in the southern hemisphere, but also some in the north. Lots of filaments in the Earth-facing zone here. Likelihood for additional coronal mass ejections or for this coronal mass ejection event to go on for an extended period of time are very high, folks. Very high. Likelihood of additional coronal mass ejections persists. And again, we may see larger and larger flares out of sunspot 2816. Those C-class flares could have appeared as larger flares had they been closer to the limb, but because they're Earth-facing, they showed up as C-class, as we can only measure the X-ray output from these sunspots in certain locations. So here's a close-up of it. Fantastic view here in 304 angstroms. And really all the wavelengths are going to show you some great detail. We only show a few per day on the Daily Space Weather. And we regularly make other playlists that contain more information. So today we'll also be talking about more exciting activity, climate insanity, and some science profanity. So next let's take a look at the location of items in the solar system. Whether they're dwarf planets like Eris, or whether they're planets. Here's where they are now. And there's where they'll be in a week. Here's a star chart. The yellow line here on my star chart is the ecliptic. I face mine to the south. I'm currently facing the south, and we've got Saturn and Jupiter above the horizon in my location. The 10.7 centimeter radio flux, the solar output of the upper chromosphere, and the lower corona, only at 78. So despite all this activity, only a radio flux of 78. And the 10.7 centimeter radio flux is 2,800 megahertz, and it coincides with 10,000 joules of flux density. Solar flux density is what a solar flux unit is. Here is the 1-year chart of the radio flux, which is this top black line here. The lower red line is the sunspot number. And NOAA is forecasting a brief period of geomagnetic unrest the night of the 23rd and early in the morning on the 24th. So that's probably a coronal hole wind stream from that small coronal hole, which is leading sunspot 2816. Next, looking at earthquakes over the past 24, we just saw a deep one come in at Fiji while I was doing show prep. But in any case, here's the list. It does not include any major quakes, although we do see some deep ones like this 4.9 near Tonga. Largest of the past 24 may have been this 5.5. I'm seeing this list for the first time myself. That was located at Chile on the west coast of South America. The geysers, California, saw a quake 100 meters above sea level at negative 0.1 kilometer depth. Peru and Fiji saw deep quakes as well. 4.1 at Peru, 4.2 at Fiji. That one coming in a half an hour approximately, 36 minutes after the Peruvian deep quake, and that Fijian quake coming in at 8:55. Volcanic eruptions are occurring also, such as Sakurajima. It's producing a 7,000-foot ash plume. 8,000-foot ash plume at Mount Ibu on Indonesia. Semeru also at Indonesia. 14,000-foot ash plume as it explodes. I believe that's an uptick at Semeru. Dakono exploding, 8,000-foot ash plume there. Some volcanic tectonic earthquakes. Veniaminoff on the Alaskan Peninsula has had the aviation code lowered to yellow, so downtick at Veniaminov. Semisopochnoi in the Aleutian Islands has been exploding, 8,000-foot ash plume above it. The Aleutian Island volcano. Popocatépetl in central Mexico, 20,000-foot ash plume there. Fuego, volcanic ash not observed in satellite. Please do not square dance around the caldera. Telica in Nicaragua, now back on the list. Low-level explosive activity has produced a 4,600-foot plume of brown ash. Ouch. Sangay exploding. Flight level 220. It's producing a 22,000-foot ash plume in Ecuador. Also Revenador in that same country, 15,000-foot ash plume as it explodes. And Sabancaya, a 26,000-foot ash plume, is a stark reminder to not pole vault the caldera. This public service message brought to you by Smash staff and I here at smashomash.com at massive personal expense and risk. So again, folks, I would remind you, please do not pole vault the caldera. But please do visit our links, such as the links that you can find at places such as smashomash.com. One of the links you may find there is our SmAsho merch link, and if you click that, it'll send you to our Redbubble shop. And we've got other designs at Redbubble in addition to the Do Not Pole Vault the Caldera product, so check that out as well. All findable at smashomash.com. The official website of the Smash News Network, least busted name in news. Let's get back to the sun-facing instruments on the GOES 16. There you can see those two C-class solar flares, which happened only quite recently. In fact, the last one was occurring as I got out of bed. We don't see any spikes in the GOES proton flux, as no coronal mass ejections have made it to the GOES 16. Here's the GOES magnetometer. And we see some pretty spiky readings here over the past 3 days, as it took a long time for the most recent coronal hole wind stream to subside. We've got a lot more information to cover here. Here's the top view ecliptic plane field plot looking at the magnetic polarity of the heliospheric current sheet, Earth's solidly in the South Pole current sheet shown in red, and we can expect the North Pole current sheet to be here at the Earth within about 36 hours. So keep in mind this data at the time of the video is 2 hours old and can suddenly change. Expecting the North Pole current sheet to be here in about 36 hours from when I made the video. And if you're wondering what time it is when I made the video, it's 5:20 a.m. on April 22nd, Thursday, April 22nd, 2021. Here's another view of the same data, the three-dimensional line of sight view, and here's the line of sight coronal hole plot. This shows you the sun's B field in blue, and we see a North Pole coronal hole. Looks like it's rotating in here. You can see it pretty well here on the last image. And that is a transequatorial coronal hole. We can expect some geomagnetism from that. Here are the filaments and the sunspot groups. Keep in mind this filaments does not show all of the filaments. There are a whole bunch down here in the southern hemisphere, and there are some not showing up in the northern hemisphere, and there are a lot more filaments than it's showing is my point. Also sunspot groups. You can see 2817 is about to lose its name as it will set in the next 24 hours over the northwestern limb. Sunspot 2816 remains significant, having produced significant flares and the stimulus for coronal mass ejections. Expect more of those. And sunspot 2818 is rather large, but still only alpha class, unlikely to produce significant flares or a lot of activity. The KP index, a measurement of global geomagnetism, is currently at 2. So calm conditions there in geospace. Next, the real-time solar wind. We just saw a couple little spikes here in the solar wind. Nothing above 7.3. Current conditions are about 6.5 protons per cubic centimeter, 431 kilometers per second is the velocity. Again, the density 6.5 or so protons per cubic centimeter. And next, geospace magnetosphere movie. Here's 4 hours of data on the magnetohydrodynamic pressure in nanopascals. It's the space weather modeling framework. And since it refreshed, we'll allow it to play through. And you can see the main pressure here on the magnetotail region as opposed to the bow shock region of the Earth facing the sun. And some minor variations here over the past couple of hours. Here are ground magnetic perturbations looking at geospace delta B. Changes to the Earth's B field. This is in nanotesla. The last one was in nanopascals. And we don't see that significant magnetic perturbations here. No real surprise there with the coronal hole high-speed wind stream having subsided over the past 24 hours. Next, I would remind our viewers that we mainly put out videos in 3 different locations, folks. Those locations are twitch.tv/smAshomash, bitshoot.com/smAshomash, and youtube.com/smAshomash. We do lots of live streaming to Twitch, and we've decided to invite Twitch for the cosmology segment, which is to follow. So here comes a cosmology segment, folks. Again, thanks to our BitChute subscribers, thanks to our Twitch followers, and thanks to our YouTube subscribers. Don't forget to check our playlists as well. Thanks to our new subscribers over on YouTube. Thanks everybody who presses share and like and so on. Please tell your friends and foes about the channel. And if you're an influencer, if you've got a big channel and you'd like to feature us, feel free to drop me a line. You can find all of our contact information at smAshomash.com and all over the internet. Here's today's cosmology segment. First on the list is the astronomy picture of the day. Today's is twilight on Earth. From the International Space Station, perhaps? Astronaut photography of Earth, probably from the space station. In any case, you can clearly tell that the horizon is flat here. The Earth is flat. The Earth is flat. Case closed. We'll talk later about how the Earth is fat and the equatorial bulge. That'll be part of the meteorology segment. Next, we'll be talking about the low-frequency array as the Outback Radio Telescope has discovered a dense spinning dead star known as a pulsar, an object only about believed to be 20 kilometers in diameter, but with massive magnetic fields, something like 1 trillion times the most powerful magnetic fields we can create here on planet Earth. And exactly how pulsars do what they do is sort of up for debate in certain sectors. So we'll kick off today's cosmology segment by talking about the, quote, giant cosmic lighthouses, end quote, known as pulsars. Anyway, there's some kind of extreme flux happening, certainly from a pulsar. Again, the magnetic fields are some of the strongest in the universe, about 1 trillion times or 1,000 billion times stronger than that we have on Earth. So pulsars are pretty interesting, and so is the LOFAR. Pulsars and LOFARs. I'm sorry, it's not the LOFAR, it's the Murchison Wide Field Array. The Murchison Wide Field Array featured on a previous video. And if you want to check out our other playlists, check out youtube.com/smAsho/playlists. We've got, I think we're pushing 200 cosmology segments now on the YouTube cosmology playlists. Next, we're going to talk about a rapidly spinning miniature galaxy. Here at the Smash News Network, we like to provide unnecessary amounts of information about cosmology to the point where it might be nerve-wracking. But in any case, here you go. It's a small galaxy, only about 3,000 light years in diameter. And I think this one actually is from LOFAR. This one's not from LOFAR either. This is from ALMA. And remember, folks, this brings me to an Einstein quote. Never memorize anything that you can look up. So we've got some gravitational lensing happening here, and I believe this is an Einstein cross right here, I believe, which is caused by distortion of light by an object in the foreground. So this little tiny galaxy is known as RxCJ0600-Z6, located about 12.4 billion light years estimated distance to this. And so it's quite ancient, as the light is believed to be over 12 billion years old. Looking at some very old photons here, folks. Some very old photons. But in any case, this galaxy is rotating, and that's interesting to know, I suppose. In any case, it's some interesting... Oh, we're looking at carbon ions here. So there you go. The radio emission spectra of carbon ions. Carbon ions, folks. And carbon is actually one of the emission spectra that the SDO uses. I believe that's 1,600 angstroms, if I remember correctly. So perhaps check out this article here on SciTech Daily about RxCJ0600-Z6. Traditionally, gas in the young galaxies was thought to have random, chaotic motion. Only recently has ALMA discovered several rotating young galaxies that have challenged the traditional theoretical framework. So the point is, folks, we don't know how galaxies and stars form. We don't know if galaxies and stars even have a lifespan, what their lifespan is, or ultimately what goes on there. Let's continue on to talk about one of the smallest black holes ever noticed. One has been discovered only at about 1,500 light years from the Earth. And what we have here is a red giant, which is a highly variable type of star. And it's being orbited by an invisible object. And basically it's causing changes to the light from this red giant. So again, only 1,500 light years away. So this object not only dark visually, but to other tools used to measure light and other wavelengths. So in any case, there's some sort of object orbiting it. This one's expected to be less than 5 times the mass of the sun. Leave us a comment if you have a theory as to what that massive radio source might be. And really, it's more of a gravitational source than a radio source in this respect, as we're not really seeing emission spectra. The velocity of the red giant and the period of the orbit and the way in which the tidal force distorted the red giant told them the black hole's mass, leading them to conclude that this massive radio source was about 3 solar masses, or 3 times the mass of the sun. Now, the way these masses are calculated, I don't want to really get into it. I don't want this cosmology segment to be too long, as this is dovetailed into the daily space weather. The next thing we'll talk about here at the Smash News Network, least busted name in news, is Cassiopeia A, the supernoval remnant, Cassiopeia A, located at about 11,000 light years. Cassiopeia A is a significant and consistent X-ray source, as you can see here in the historic graph going back about 16 years. And we actually just about 10 days ago saw quite a beefy outburst here. One of the ones that would be well off of this scale, a huge X-ray burst from Cassiopeia A, the supernoval remnant. So let's take a look at it in some wavelengths, and before we go to wavelengths such as this infrared imagery, let's take a look at the electromagnetic spectrum. So the electromagnetic spectrum, we're talking about photons here, folks, photons. And the frequency of the photons determines what type of electromagnetic radiation it is. So the wavelength, frequency, the amount of energy, also associated with different temperatures, as you can see here. And you're talking about, radio waves can be the size of buildings or humans, microwaves about the size of a honeybee, infrared light about the size of a pinpoint, visible light about the size of a protozoan, ultraviolet the size of a molecule, and so on up to gamma rays. And we've even talked about petatrons on the channel. Perhaps, again, check out our older cosmology segments. Petatrons. So here's Cassiopeia A, the supernoval remnant, and right now you're just looking at it in heat. So this is infrared light, folks. So the infrared light from the sun is some of the light that makes it all the way to the surface of the planet. It's what feels warm when the sunlight hits you. Anyway, there's the infrared spectrum, and let's take a look at this in the ultraviolet spectrum. You can see the way it doesn't really show up as much at all in the ultraviolet spectrum, but on Chandra, Cassiopeia A looks like this. So now you're looking at X-rays, and you can see how vastly different Cassiopeia A looks. Well, to make things even more interesting, here's some spectral analysis of Cassiopeia A. And what you're looking at are different emission spectral states here of various different chemicals. The article we're talking about in this cosmology segment is the titanium, which coincides with these light blue areas. So you can see lots of titanium in this area here, some titanium hotspots here and over here. And ultimately, the real question is, folks, where does the titanium come from? Does it come from deep within the cores of stars? Or is it happening out on the surface of stars or someplace in the atmosphere? Or is it perhaps happening between the atmosphere and the surface of stars? In short, the answer is we don't know. But in any case, this article here is on phys.org's Astronomy and Space section, and there are articles all over the internet about the titanium in Cassiopeia A. So now there's a lot of reasoning to be paying attention to astronomy and cosmology right now, as physics itself is sort of being rewritten in a lot of ways, especially with the emerging, how can I say it, the emerging horizon of superionized material, condensed matter physics, folks. It's getting pretty interesting. And so, quote, when the supernova happened, titanium fragments were produced deep inside the massive star. The fragments penetrated the surface of the massive star, forming the rim of the supernoval remnant Cassiopeia A, said co-author Shigehiro Nagatake of the Riken Cluster for Pioneering Research in Japan. Our research could be the most important observational result probing the role of neutrinos in exploding massive stars since the detection of neutrinos from supernova 1987A, the most famous supernova, said co-author Takashi Yoshida of Kyoto University in Japan. So again, you'll see this one all over the place. The results have been published in Nature on April 22nd. And again, you'll find this all over the Science Wire. Interesting stuff happening regarding the titanium, which coincides with these blue areas of Cassiopeia A. And if you're wondering what the other chemicals are, the other chemicals are the orange is iron, the purple is oxygen, silicon to magnesium ratio is green, and titanium is light blue. So that article there is on phys.org's Astronomy and Space section. And that's today's Cosmology segment, the official cosmology segment of the Smash News Network, least busted name in news. And by Twitch, we'll be back for the meteorology segment. Next, continuing on with the daily space weather. Here's the electron flux over the past year, and you can see very high levels of electron flux. We made it to about 14 times warning levels yesterday, and we're back well into warning levels once again today. Very high levels of electron flux. Expect significant GPS errors, especially around the equator at noon. Here's the forecast model. The forecast is the green boxes. The forecasts are the green boxes, and the yellow diamonds are not Lucky Charms marshmallows. Those are the observations. Here is the diagram of the Van Allen belts. Keep in mind distances are shown here in miles, and we're showing you this because we're going to show you the total electron content next. So here's the total electron content forecast, and we're seeing pretty organized electron blobs here. Actually, significant GPS errors happening at night there over places like the central Atlantic Ocean. So pretty disorganized electron flux right now. These zones, especially over the central Atlantic there, lots of nighttime GPS errors happening there. Here's another diagram of the atmosphere. This one's showing you the F ionosphere layer. We use it daily to show the location of the F ionosphere layer. It also shows you the penetration of electromagnetic radiation. As you can see, visible in infrared, make it all the way to the surface. Near UV is mostly filtered out by the troposphere. Middle UV is mostly filtered out by the mesosphere, and so on. Actually, mostly filtered out by the stratosphere anyway. Continuing on, here's the ionosphere map. And it's going to switch back to tomorrow right here. I mean, to yesterday, rather. I've become a Time Lord, folks. We have become a Time Lord here at the Smash News Network. And it all has to do with patrons and YouTube views and so on. Probably also with algorithms and other things that are completely beyond our control. Anyway, here's the latest image of the ionosphere, which is looking quite discharged, actually. Ionosphere looking quite discharged over the past 24. So we see very small concentrated blobs of frequency vibration here. You're looking at megahertz. Each blob coincides with 1 megahertz. In other words, the bright green portion is 5 million vibrations per second. Here's the latest image, which is from 9:30 Universal Time, looking normal there. Let's talk about climate. And since it's time to talk about climate, let's welcome Twitch back. So this will be our meteorology segment for the day. Let's talk about snow and ice. Yes, snow and ice. Now, everybody's very scared and spooked by climate nonsense. What you're looking at here is a glacier, and this looks like the transition between a glacier and sea ice. One of the many things you may see on the internet attempting to frighten you into thinking that the ice is melting is you'll see videos of calving events where a glacier is falling into the ocean. You know what causes that, folks? It's caused by lots of snow and ice uphill from the glacier, which the weight of which cause the glacier to be pushed into the ocean. It's called a calving event. It's caused by lots of ice. When a glacier melts, it recedes uphill to the mountain, from which because it's a river of ice, it recedes uphill like an evaporating river. It doesn't calve into the ocean. That's an indication that there's lots of ice. So that's just a preface to what we're talking about here. As here at the Smash News Network, we prefer to provide objective, reasonable information as opposed to climate nonsense, like certain organizations, CNN. So here's the first story. Earth's cryosphere is vital for everyone. Why? Well, the albedo effect. Gee, we wouldn't want too much sunlight to reach the planet. Boy, that would be very dangerous. Now, I don't know if you're aware, but you're actually living through an ice age right now, folks. Yes, it's true. You're actually living through an ice age. What is an ice age? Well, an ice age is defined when the planet has 2 icy poles all year round. Now, if you remember, back in the late 80s and mid-90s and so on, and even going on to this day, people have been forecasting an ice-free Arctic and Antarctic and catastrophic sea level rise enveloping cities and making the planet very, very scary and very, very spooky. You're living through an ice age currently because we have persistent ice at both polar caps. So let me just continue here. As we'll be talking about Earth's gravitational pull and centrifugal force and snow mass balance and all kinds of stuff like this. So let's read a quote from the article. Between 2003 and 2019, the Greenland ice sheet lost an average of 200 gigatons of ice per year, the researchers concluded. Antarctica's ice sheet lost an average of 118 gigatons of ice per year. The combined ice losses caused sea levels to rise by 0.55 inches over those 16 years, allegedly. Okay, let's talk about that. First of all, let's talk about the Earth's rotation. Earth's rotation has been speeding up. We've seen the fastest Earth rotation in 2020 that we've seen since the 1960s. And what's causing it? Well, the most likely explanation of what's causing it would be global cooling. Yes. Because, you see, when Earth's equatorial bulge shrinks, that causes the Earth to rotate more quickly, which means if the oceans get cooler, they recede as cold water takes up less volume than hot water. But also, when water gets deposited, instead of at the equator, it gets deposited at the poles in the form of snow and ice. Guess what happens, folks? The Earth's rotation speeds up the same way a spinning figure skater speeds up when she pulls in her arms. When the Earth's equatorial bulge shrinks, the Earth speeds up its rotation. Now, this is shown by the geologic record and by eclipse data. Here's an article about it, reconciling past changes in Earth's rotation with 20th century global sea level rise, resolving Monk's enigma. So perhaps check this one out. This one is from 2015, but there's all kinds of information you can find out about this, folks. So perhaps check that out. Next, let's check out the snow water equivalent. You can see the way this was 2 standard deviations above normal at the peak right around here in mid-March. Now the snow extent, which is just the square mileage that the snow covers, hasn't really been that high. It's pretty much been in the 1 standard deviation range basically the whole time, except during late October. But you can see it's been quite in the 1 standard deviation range, the snow extent. Next, let's look at the snow mass. The 2020 to 2021 winter was the 4th winter which featured at least some point 2 standard deviations above normal snow mass balance. So what is this deviation above normal? Well, this deviation above normal is, well, will you look at that? It's just about 200 gigatons outside of the 1 standard deviation range. And it's even more than that. I don't know, 400 gigatons outside the average, which is the dotted line here. So, oh no, 200 gigatons have melted from the Greenland ice sheet, which is where most of the snow... Is this making sense, folks? Anyway, here's the current state of affairs. This one is as of December 29th, 2020. What? What? All right, here's the Rutgers snow extent. As of, for goodness sakes. Is it going to show me a date? It is not going to show me a date. We'll just show you on windy.com. So before we go to nullschool.net and look at that stuff, let's go to windy.com real quick. And here's the current state of affair for snow depth. You can see Ohio, the entire northern half of the state is covered in snow, with several inches south of Lake Erie. Also, West Virginia's got some snow, most of New York. Half of New Hampshire, Vermont, Maine, all covered in snow. Even western Massachusetts has some snow. And let's get back to the regularly scheduled meteorology segment. So next thing we're going to look at here, folks, are the jet streams. So the reason it's so ridiculously cold in the eastern portion of the U.S., in fact, the entire 2/3 of the U.S., I guess you could say, is because we've got 2 different portions of frigid jet stream air pulling in. So you not only have this jet stream area here from central Canada pulling cold air straight down into the, into the Great Lakes region, but you've also got this air from British Columbia coming straight from the polar region and spreading some chilly temperatures. So perfect example of meridional jet stream flow. Also, look at these huge bends in the jet stream here in the northern hemisphere. The source of your cold temperatures. Here are the jet streams of the eastern world. Since we showed you the west, here's the east. And we'll show you surface winds as well. There are the surface winds. Has this system actually increased? Doesn't look like it has. It looks like it's weakened a little bit. I see 80-mile-per-hour winds. Looks like it's weakened a little bit. At least its connection to the jet stream has weakened a little. And we'll show the surface winds of the western world as well. There are the surface winds of the west. lightningmaps.org for a real-time lightning map. And by the way, I actually accessed lightning maps yesterday. I was in a thunderstorm, and I broke out lightningmaps.org. It showed me that the lightning was well north of my location and of no real concern. Real-time lightning maps at lightningmaps.org. Climate tipping points need not be the end of the world. Disastrous consequences could be averted. Whether it's the idiotic idea of carbon sequestration or the idiotic idea of solar atmospheric radiation, solar radiation management, whatever it's called, geoengineering to put dust in the stratosphere to reflect sunlight back into space. They're both idiotic ideas. The idea that man can control the climate is just absolutely ridiculous. If you know anything about the wattage requirements that are required to control the environment, whether it's through whatever idiotic ideas that you have that mankind can and is controlling the weather and indeed the climate, is just absolutely ridiculous. It's a pathetic and putrid excuse. And it's ridiculous, nonsensical arrogance of the highest order. The idea that mankind can control the climate is absolutely idiotic. And here's an article about it. about climate tipping points need not be the end of the world because, we'll just control the climate. No big deal. Don't worry about it, folks. We'll just control the climate if we need to. A skill mankind does not have. Again, here's the current snow situation. Let's advance this till tomorrow. There's where we expect snow to be tomorrow at noon. Continuing on. Check out the weather.gov map. We've got freeze warnings. That's all those purple regions, folks. Frost advisories are these blue regions. Hard freeze warnings in Maine. Oh my God, it's so hot that it's cold, folks. It's so hot that it's cold. Here's your temperature anomaly. And these purple areas are like 15 degrees Celsius below normal. 15 degrees Celsius below normal. Let's advance this. Here's Friday, still cold. And by Saturday, we get more normal temperatures, but another ultra cold wave moving into Montana, North Dakota, South Dakota, and Minnesota by Saturday. Here's the current U.S. Doppler radar map, and we've got snow falling in Pennsylvania, New York, Maine, New Hampshire, Connecticut, Massachusetts, Vermont, Ohio, Indiana, Wisconsin, Illinois, Michigan, Iowa, Minnesota, Nebraska, Kansas, Wyoming, Utah, and New Mexico. Oh my God, folks. It's so hot that it's cold. It's so freaking hot that it's cold, folks. Stop the presses. Oh my God. Here's what's going on in the cloud layer. Better make the planet cooler, folks. The planet's not cool enough yet. We got to cool the planet off because it's so hot, folks. So hot. Cloud layer. Water vapor map, a cloud layer, a water vapor. And once again, there's the U.S. Doppler radar map. There's the cloud layer. It's the NASA GOES 3.9 nanometer interactive weather satellite. There's the water vapor. And that's today's meteorology segment. I've been your host, Dan, a.k.a. smAsho. Thanks for tuning in. See you later, Twitch. Let's get back to the daily space weather. Since we've got bonus features, we've got to show you those and close this thing out and get it uploaded. First, the imagery from El Teide, Spain. So here we are in hydrogen alpha. It's the National Sunspot Observatory. It's quite new data, and you can see massive filaments both in the north and south polar regions. Likelihood for coronal mass ejections, additional coronal mass ejections continues. Thanks, SMASH team, for tuning in. Here come more bonus features. It's the colorized magnetogram and the intensity gram. Sunspot 2817 about to set. Sunspot 2816 looks like it's degraded a little bit. Sunspot 2818 remains a single alpha class umbra. Large but not particularly active. Before we close things out, I'd like to talk about our mission. You can read all about it at smashomash.com/forum/mission. The number one item is to assist, study, and report on the ongoing formation of a unified theory of physics, to raise the awareness of the general public of the relationship between space weather and Earth effects, to connect and consult with media organizations to multiply our reach, to demonstrate cutting-edge proof-of-concept solutions to problems, to publish scientific papers in a multidisciplinary manner, such as explaining the mechanism behind the solar sunspot cycles and solar polar field reversal cycles. That's going to be a thing pretty soon. To assist mankind by advancing the study of predictive phenomenon in order to optimize value and reduce risk and liability and save lives and resources and adapt no matter what the adversity is, and to not be ossified in our beliefs and to treat those who are with love, respect, and inclusion to the scientific discussion. Thanks to our patrons, the main people out there that are actually helping us on our mission. Please consider doing so yourself at patreon.com/smAshomash. It's patreon.com/smAshoMash. Thanks again, patrons, for helping to advance this mission, which is not the easiest thing to do. And we'll close things out by looking at the sun in 171 angstroms. Great view of the solar flare coming out of sunspot 2816, right in the Earth-facing zone there. And here's the western limb in two wavelengths, 193 and 171. And here's a close-up of sunspot 2817. Thanks again for tuning in, folks. Remember, stare at the sun. Attempt to understand the physics. And since it'll never be now again, may that solar wind be at your back.